Modern physics relies on the massive scale of the particle accelerators at CERN. Yet, even with miles of superconducting magnets and high-energy collisions, the theoretical apparatus still rests on a classical assumption about time. When the pioneers of quantum mechanics codified the rules of the subatomic world, they treated time as an external, immutable clock ticking in the background. In the standard Schrödinger equation, the variable t functions as an independent variable. It is a slider that moves forward at a constant rate, regardless of the state of the wave function it describes. This creates friction when modeling highly cohesive, self-organizing dynamical fields. If a system is defined by internal coupling, an indifferent, detached clock fails to capture the mechanics of its evolution. The A framework offers an alternative. Time is redefined here as a strictly emergent property, rather than a primitive background parameter. In this model, time arises from the continuous evolution of internal phase, structural coherence, and the accumulation of phase entropy. This results in a mathematical hierarchy of time. It maps the progression from an abstract phase increment, tau, through intrinsic field time, Ta, eventually arriving at the physical time of our observable reality. Time is not the stage for physics. It is a structural byproduct of the field's internal dynamics. To derive this timeline, we first have to move past the standard U1 complex phase representation used in quantum mechanics. Standard theory models phase as a simple vector rotating on a two-dimensional complex plane. The phase angle, phi, moves along a one-dimensional circle. This geometry is sufficient for tracking isolated or weakly interacting quantum states. However, the AE model views the universe as a dense, non-commutative network of coupled oscillatory nodes. When a simple one-dimensional phase angle is forced to govern simultaneous, multi-axis rotations in a continuous field, the coordinate system fails. This is the same mechanical failure seen in Euler angles. If two of the three independent rings align during a complex rotation, the system loses a degree of freedom, resulting in a singularity known as gimbal lock. The math physically breaks down because a one-dimensional phase cannot encode the nested three-dimensional orientations required by a coupled field. If reality is a web of interacting vibrations, we need a geometric upgrade that can handle multi-axis rotation without failing. The solution is the Quaternion. Expressed as Q equals A plus BI plus CJ plus DK, this four-dimensional structure provides the necessary degrees of freedom for complex rotation. By applying a unit constraint, the geometry is forced onto the S3 manifold, a four-dimensional hypersphere. S3 geometry allows for smooth, singularity-free rotations across multiple axes simultaneously, establishing a continuous SU2 symmetry. We can now physically model the entire A field as a vast, interconnected network of these non-commutative quaternionic nodes. Each node's quaternionic state encodes its local phase and global spatial orientation in one unified value. This ensures that phase structures evolve through continuous rotations, maintaining the internal consistency of the field as it reorganizes. This plot from the model demonstrates the result. The central peak represents the coupling intensity, where organized phase relations form a stable, persistent structure in the field. Quaternionic topology provides the geometric fabric needed to sustain these complex phase dynamics. With this internal geometry established, we derive a temporal flow without relying on an external clock. We define the intrinsic rotational rate, omega A, as the norm of 1/2 the imaginary part of Q inverse times its time derivative. As the system rotates, it traces a path across the S3 hypersphere. The accumulated topological distance along this path is defined as tau A. This utilizes holonomy, the idea that time is the integral of phase rotation along a specific trajectory. The explicit integral for A time is the integral from 0 to t of this rotational rate. Time is now rigorously defined as arc length in the system's internal state space. This removes the need for an external observer. The system's own internal movement generates its own timeline. At the most fundamental level, intrinsic time measures how much the system's internal phase has rotated. The final step is translating this abstract mathematical arc length into the unidirectional physical time, t-phys, that we experience at the macroscopic scale. This transition is governed by two variables, structural coherence, C, and phase entropy, S phi. These variables share a dual relationship. Any change in coherence over time is balanced by a negative change in phase entropy. Because the model adheres to thermodynamic constraints, phase entropy must strictly increase over time. This unavoidable growth of entropy degrades phase synchronization, causing the field's internal structures to scatter. In the AE model, this irreversible loss of structural coherence is what creates the macroscopic arrow of time. This results in the deformed temporal algebra. The physical time derivative is defined as the intrinsic phase derivative rescaled by the exponential of entropy and the square root of coherence. High coherence makes evolution slow and smooth, while high entropy accelerates it. This forces a departure from standard Hamiltonian mechanics. While classical models assume time as an external constant, the AE framework treats the temporal operator as a dynamic function of the system's internal organization. Physical time is no longer a background constant. The rate of change for any given system depends on the informational coherence of its local field. Time is not a separate dimension. It is the structural memory of its own decay and continuous phase rotation. Time is what the system does.